Let me recall that J is equal to L minus half, and we are starting for this J value, and there will be two combinations, L and S equal to minus half, and one other combination will be L minus 1 and S equal to plus half. And the magnetic moment, this should be Z. The average value of the magnetic moment of the nucleus will be A square. A square is the probability of the contribution coming from psi 1, B square is the probability of contribution coming from psi 2. So mu Z is A square into combination, contribution from psi 1 state, and B square into contribution of psi 2 state. So A square and B square, what we have found here, just write a couple of moments before. These are the A square and B square values. A square plus B square should be equal to 1 because these are the probabilities. This will add up to 1. And now I am going to put the values for psi 1 and psi 2 contribution of mu Z. That is the values of the mu Z for psi 1 state and psi 2 state. Let me make it upwards, the paper. Let me recall that J is equal to, we have done some algebras here, and we are where you could get starting for this I have multiplied value twice L with this one. There will be two combinations of this bracket. L, so it's and GL S equal to minus half minus GL other combination will be L minus 1 and S equal to here we got 2 L square GL the magnetic moment GS into L, and this is the common factor. The average value of the magnetic moment of the nucleus twice L, 1 plus twice L is square. A square is the probability this of the contribution coming from psi 1. B square is the probability both A contribution and B. A square and B probability of contribution coming from psi 2. Now I am getting this one. Z is this value square into combination expression for contribution from psi 1 state and B square into contribution now of for J equal to L minus half. A square and B square what we have found here half. Just write a couple of moments before putting these are the A square and B square values. A square plus B square should be equal to 1 because these are the probabilities. This will add up to 1. And I need to replace it here too. Now I am going to put the values for psi 1 and psi 2 contribution. We have of mu Z into this. That is the values of the relation for psi 1 state and psi 2 state. The magnetic moment of the nucleus make it upwards to GL into 2J and these are the some algebras. We have done some algebras here and mu 1 where you could get by twice J plus I have multiplied twice L with this one. Let me have and a look. I have opened up this bracket. So it's GL into again. L minus GL plus GS by 2. And here we got 2 J equal L to L minus square GL minus for proton GS into L, and this moment. Is the common factor mu N get by 1 plus twice L. 1 plus twice L values coming from and GS. This two and after terms calculation 1 plus twice L is common. We got both A and B for a particular state having spin total spin J. Now I am getting this one. The magnetic moment. This value formula. Of the magnetic this expression for of mu Z average value, and this is now for J equal to L minus half will give me L equal to J plus half. For neutron, one thing we need to keep in mind that we need to put GL equal to 0 for a neutron. So this and this are the average value of the magnetic moment for proton and neutron respectively for J equal to L minus half state. Recalling the value of the average average magnetic moment mu Z for proton and neutron, what we have discussed earlier. These are the values for J equal to L plus half. We have also calculated the general expressions for J equal to L minus half. we can plot the values of this mu z with the j values. Now, as we can see, for j equal to L plus half, for neutron, this is a constant value. It does not depend on j. So, for neutron, these values should not depend on j. So, for j equal to half, 3 half, 5 half, 7 half, or whatever, mu z is a constant. But if we put the value for proton, we'll get this type of points. And we can make roughly a straight line for protons. But these are actually the theoretical predictions. Experimentally, what we have seen is the value of the magnetic moment oscillating or fluctuating like this. So the estimation what we have made in the single particle shell model is, suppose there are 7 neutrons or 7 protons, the 6 will make a pair and will not contribute to the magnetic moment. Only the 7th neutron or the 7th proton, that is the lone pair nucleon, will only contribute to the magnetic moment of the nucleus is not correct, because that assumption does not lead to the matching of theoretical, which are these theoretical values are called Schmidt values, and the matching of these theoretical Schmidt values and the experimental values is not quite good, as we can see. So we need to now consider the contribution of other nucleons also.